In today's video, we're going to be looking at and trying to debunk all of set theory. Set theory is the current foundations of modern mathematics. And we're going to be using some ideas here that are mine and some ideas that are Steve Patterson's. So if Steve Patterson claims intellectual credit for any of the ideas in this video, he's probably right. It probably is his idea. Now, if you remember previously, I made a video on set theory, and if you've already seen that video, I wouldn't watch this one. It's going to be repeating probably most of the same points. I wanted to make this video so that it would be separate from the Bertrand-Russell paradox, because in that combined video, everyone was just talking about the Bertrand-Russell paradox, and nobody even got to set theory. So this one, hopefully some people will actually get to set theory, and we can actually examine some of these ideas and see if they make any sense. So let's try to get into this as fast as we can. Now, if you already know how set theory works, then just skip forward a bunch here, because I'm just going to explain the basic ideas. So first term we need to learn is a cardinal number. Actually, no, sorry. The first term we need to learn is a set. A set is like a grouping or category tool, right? So you could think of it like a folder on a computer, but a set can contain anything. For example, I could have a set of everything that's blue. I could have a set of everything that's blue on Earth. I could have a set of all numbers larger than 3. I could have a set of all numbers between 4 and 7. I can make a set of pretty much anything. I can have a set of you, right? I can have a set of you. It's just going to contain you, one you, and that's it, right? So this bag thing here is kind of like a set. You could think of it like a folder, whatever. A bag is an easy way to visualize it, right? So it's just this container that holds virtually anything. I could put an idea in there. I could put a physical object, whatever, right? So it's a really, really, really broad. Now, next thing is cardinal number. So a cardinal number is the amount of elements in a set. And each element has a value of 1, right? So for example, these bags contain candy. I'm making this video near Halloween, so I'm thinking a bit about candy here, right? So what's the cardinal number? What's the cardinal number of each bag here, right? This one is 1, 2, 3, 4, 4, right? And this one is 1, 2, 3, 4, also 4. So both of these have the same cardinal number. Now, bijection is this system where we pair each element of each bag in one-to-one correspondence so that we count everything in both sets. That sounds very fancy. Let's put that into a very simple way of understanding it. Let's just do it here. Okay, so we take one element out of this bag and we pair it to an element of this bag, right? We take an element out of this bag, pair it to an element of this bag. We pair this to this and this to this. And since everything pairs off one-to-one, we can therefore say that there is a bijection between these two bags, right? Okay, this one has a bijection. Now, if I added one more Twizzler or whatever into this bag, we would not have a bijection, okay? Because obviously they would not all pair off. We'd end up with one extra element in this bag, okay? Pretty simple. So set theory makes very good sense, and it's pretty rational until we get to this concept of infinite sets, which is what set theory is actually all about. If we use finite set theory is just fine. There's actually no issues with it. But infinite set theory is where we're going to have huge problems. All right, so now we're going to get into infinite set theory here. It's pretty much the same as finite set theory. They apply the same logic, but then you get a lot of problems here. So Cantor's logic all relies on this idea here, which is if you can find any one bijection between infinite sets, they are also the same size. Meaning if you can pair off an infinite set like one-to-one like this, ding, 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 and everything gets used up in both sets, then we can say that these infinite sets are the same size. Or if we pair them up and let's say we end up with some remainder on this one and everything on this side gets used up, then we could say that this set is larger than this set, right? Well, that works good and all for finite sets, because if you can find any one pairing between a finite set, like let's just say I have my little bag here and this one here, order doesn't matter with finite sets. So for example, I could pair it this way, or I could pair it this way. It wouldn't make a difference. You'd still get, like, finding any one bijection proves all pairings are going to produce a bijection, right? You find a single bijection, it means that any order will produce a bijection. That's not true with infinite sets. Okay, you can pair them in one way, which produces a bijection, and in another way that does not produce a bijection. So let's just do that to show what the hell I'm talking about here. Okay, that might sound a little confusing. So right here we have all natural numbers. I always put an N there for natural numbers, and here is all even natural numbers. All right, 2, 4, 6, 8, 10, all even natural, and then natural 1, 2, 3, 4, 5, 6, 7, and these lists go on and on forever, right? So what Cantor reasons is essentially that you can pair 1 to 2, 2 to 4, 3 to 6, 4 to 8, and these lists will go on infinitely, and you can just keep going horizontally like this. This list will never run out, this list will never run out, and therefore you can use this method to pair them all off and say that even naturals is equal to naturals. Now that sounds pretty weird when you actually think about it. If we're going to say infinities can be different sizes, shouldn't the infinity of all natural numbers be bigger than the infinity of just even natural numbers, right? And Cantor would say no. He would say they're both aleph null. Okay, so this is the symbol for infinity, and this is 0. So infinity 0, aleph null is the smallest infinity you can have. He would say they're both aleph null. All right, so this here is an algorithm to pair any set in one-to-one correspondence where you count every element in every set. This is just going to change the order in which we pair things, right? So we make two lists, list 1 and list 2. Everything that is identical, we put in list 1. So 2 is identical to 2, right? 4 is identical to 4. So we would have 2 and 2 here, and we'd pair that off. We'd have 4 and 4 here and pair that off. And we'd have 6 and 6 here and pair that off, etc., right? And in list 2, we pair all non-identical elements. All right, so this one we're going to have 1, 3, 5, 7. Everything that's odd. And obviously, none of the numbers in list 2 are going to get paired off, and everything in list 1 is going to get paired off. So this is a perfectly valid way to count every element in both sets and pair them off in one-to-one correspondence. But doing this will not produce a bijection. So now, this logic is just wrong, because finding one bijection doesn't prove that these two infinite sets are the same. All right, next, this is Cantor's subset argument, which is that the subset of an infinite set is a higher infinity than the set. And the way you mathematically compute the subset is 2 to the power of x. Okay, so let's look at this with a finite set, and it's going to make some sense. What does all that mean? So, all right, so let's take a look here. This is our set. We have 4 elements. The cardinal number is therefore 4, right? And according to Cantor's idea, 2 to the power of 4 should therefore tell us how many subsets we have. So what is a subset? A subset is every arrangement of the set excluding order, including nothing and including everything in the set. So that might sound a little confusing. Here's a list of all the subsets of this set. All right, this is every possible arrangement you can have of these numbers, excluding order. So for example, 2, 3, 4, you wouldn't have an extra one going 4, 3, 2, right? That would not count as an additional subset. So let's test it slightly. Let's cross out an element. We're going to cross out 4. So now everything with 4, every subset with 4 also gets crossed out. Okay, that is a 4, 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 that is a 4. And now we should have 2 to the power of 3, which equals 8. We should have 8 things left. Is that right? Yeah, 1, 2, 3, 4, 5, 6, 7, 8. 8. Check. Now, there's probably a better way to mathematically prove that this formula is correct, but we're just kind of proving it through evidence, right? And all right, so now we're going to get to this infinite sets here, okay? So we're going to take the first infinity, which is aleph 0, and 2 to the power of aleph 0 is the subset of aleph null, right? So this is aleph null, the smallest infinity. 2 to the power of aleph null is the subset of aleph null. And this should be larger. This should be a higher infinity than aleph null. If you do this, you're going to get aleph 1, right? Aleph 1 is the next biggest infinity, then Aleph 2, and so forth, right? So 2 to the power of Aleph 0 is Aleph 1. So far, so good, no real problems. Now, another way we could simply write this out is 2 times 2 times 2 times 2 times 2 infinitely long, right? 2 to the power of infinity just means 2 times 2 times 2 times 2, no problem there. And this also will equal Aleph null, or sorry, Aleph 1, right? Now, when we get to 2 plus 2 plus 2 plus 2 plus 2, this actually does not equal Aleph 1. This actually equals Aleph 0. All right, so we can simply write multiplication as repeated addition, right? So a simple way to write this is, well, 2 times 2 times 2. Well, 2 times 2 is 4. 2 times 2 means 2 plus 2, right? This is the same as that. And this is the same as well. So we're doing 2 plus 2 twice, right? So this statement here is the exact same statement as this. So what I'm proposing is that using brackets, we could write this 2 times 2 times 2 times 2 out as a repeated addition statement, right? Adding brackets doesn't change anything, right? Adding brackets is not going to change the value of this infinite series, right? Adding brackets simply changes the order in which you add things. It's not going to change the value. Just more or less follow the same process. We're going to keep bracketing it. We'll add a third bracket here, and then there'd be another bracket over here for the next. There'd be 3 over here, and so forth. So using brackets, we can simply write the expanded version of this as an addition statement. And this addition statement is going to be exactly the same as 2 plus 2 plus 2 plus 2 plus 2. So we can prove that this is actually the same as this, but they produce different infinities, even though they're the exact same thing. So this shows us that this subset law is probably wrong. All right, so this brings us to Cantor's next argument, which is the snake argument, right? And this is the idea that rational numbers are an equal size to all natural numbers because you can produce a bijection through the snake argument. Okay, so how does this snake thing work? So we have a list of all rational numbers, and rational numbers, if you remember, they're fractions. So this list here will cover every fraction there is, all right? 1 over 1, 2 over 1, 3 over 1. You know, think of any fraction you can imagine. Like, let's just say, I don't know, 6 over 2, right? Well, we get to the 6th column here, and the 2 here, that's going to be 6 over 2 here, right? Or say 1 over 3, I don't know, whatever, right? Is that going to be on our list? Yeah. This system will successfully list out every single rational number. It's a pretty cool way to do it. And therefore, what Cantor says is that you can use this snake method like this. So we draw a line like this, and using this snake method, we'll be able to pair the first number here to 1, the second number on the snake to 2, the third number to 3, the fourth number to 4, and so forth, right? We'll be able to draw this line and turn this into we'll basically be able to turn this 2-dimensional list into a 1-dimensional line and pair it to this number line here of all natural numbers, and therefore we've produced a bijection, and therefore this statement is true, according to Cantor's logic. But again, the problem, when we go back to the beginning of set theory, is finding a bijection does not prove that 2 sets have equal cardinality. All right, so now we're going to try to debunk this snake argument. So what we're going to do is we're going to take our natural number line and we're going to rotate it sideways. And we'll notice that this is actually the exact same row as here, okay? And we're going to use this pairing method here. Okay, so if row 1 and row 2 are bijection, then move to the next row. If not, add the remaining elements to the next row. So, meaning we're going to pair this row to this row. We're going to pair row 2 to row 2, right? Row 3 to row 3. Obviously, this method will count every element of both sets. And this should be a valid way to pair everything in one-to-one correspondence, right? Now this first row is obviously going to pair off perfectly to this first row. Obviously this has to produce a bijection since it is the exact same number line, right? The first row here is literally the list of all natural numbers. So obviously this will pair off perfectly. There won't be any remaining elements, right? We won't be adding anything from this list to the next row. So after we're done pairing the first row, we're already out of numbers here, and we have a bunch more numbers here. So this is wrong, right? All right, so this is Cantor's diagonal argument here. And the diagonal argument is that the list of real numbers between 0 to 1 is larger than the list of all natural numbers. It's a higher infinity. So natural numbers would be Aleph 0, and real numbers would be Aleph 1. And we're going to get into why that is here, according to Cantor. So this here is a list of every real number between 0 and 1, right? This ... implies that it extends infinitely this way, and this list also goes down infinitely this way as well. So with the diagonal, what we do is we take the first digit of the first number, we take the second digit of the second number, we take the third digit of the third number, the fourth of the fourth, the fifth of the fifth, and sixth, and yada, 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 yada. You get the idea, right? And then we write this out as an actual number. So in this case, we get 0.054357767. That's all the numbers we just highlighted as this number here, right? So this number will go on and on and on, right? As we add more to our list, the digits will keep increasing. So what Cantor says is that you change each number on this list any way you want. It doesn't really matter how. So a very simple way to do that is we just add 1 to every digit, right? So we get 0.1, 0 becomes 1, 5 becomes 6, 4 becomes 5, 3 becomes 4, 5 becomes 6, 7 becomes 8, and then 7, and then 8 again, right? So now this new number that we're producing here, this is this special number, which is a real number, right? It's going to be a real number, but it's not going to be on the list of all real numbers. So we're making a real number that's not on the list of all real numbers. That sounds impossible. So let's examine this logic. So according to this logic, well, it can't be the first number on the list because the first number is going to be different than this first digit here, right? It can't be the second number on the list because the second digit here has to be different than the second digit on the second number. Using this process, we can determine no matter what, this number cannot appear on this list because it's different than every number on the list. We have created a real number that is not on the list of all real numbers. Well, this is almost like a paradox on its own, right? What have we done here? So it's some interesting stuff here. Okay, so what's going on here? Either the diagonal is not a real number. Number 2 is that the list is not completed. We don't have a full list of every real number. Or 3 is that logic itself is broken and doesn't work. And okay, I think the very clear and easy answer to this is number 2 here. The list is not complete. And that makes good sense because it's impossible to complete an infinite list. By definition, infinite is that which cannot be completed. So I think Steve Patterson's logic here pretty easily resolves this, okay? We can't complete an infinite list, otherwise it's just not infinite. So with this diagonal number, what exactly is going on here? Well, what's interesting about this number is it's a lot more like x. It doesn't have a really clear value. Like pi has a clear value, 3.14, right? E has a clear value, 2.7182, blah, blah, blah. 1/3 has a clear value, 0.333 has a defined value. Whereas this diagonal will actually change its value. And what happens is, as we extend this list longer and longer, the diagonal is always kind of one step ahead of the edge of the list. And the only way you're ever going to reach this diagonal number is by completing this infinite list. And you can't complete an infinite list. All right, so a similar equivalent we could use with natural numbers would be this S number, okay? So this S number is the sum of every number on your list. So if I have this list, 1, 2, 3, 4, 5, 6, 7, 8, well, this S number is a natural number. This is natural numbers here. This S number will obviously be a natural number because it's a sum of a bunch of natural numbers. And if we added up all the sum of these numbers, I don't know, maybe it'd be like 32 or something, and 32 would be our S number. But the problem is when we have an infinite list, this S number will always be one step ahead. Every time we add a number to our list, this S number will be like over here. It grows faster than our list. So if we move this list in this like continuous direction larger, right, this S number will never appear. And, by Cantor's logic, you could say, well, therefore natural numbers have this extra dimension, this S dimension, which allows us to create this number which will never appear on a natural list. But it should be a natural number because we're adding just a bunch of natural numbers. And the same thing is going on here. If we can complete the infinity, then we can have this S number on the list. But that's a contradiction because the definition of infinity is that which cannot be completed. So this logic is all just wrong. All right, so what do you think? Do you think that set theory is rational, or do you think this is just some bad logic? And I'll leave you with this final quote here. This is from Leopold Kronecker from Göttingen University. Das ist Theologie.